Section: Introduction. In this section, we delve into the fascinating world of deep reinforcement learning, RL, which marries traditional reinforcement learning algorithms with the power of deep neural networks. This combination has been remarkably successful, enabling agents to tackle complex tasks with a proficiency that often surpasses human capabilities. Despite their success, the intricacies of how deep networks function within RL and how they learn remain largely enigmatic. Interestingly, recent studies have unearthed some unexpected behaviors when deep networks are applied in RL, which starkly contrast with the patterns observed in supervised learning. For instance, while larger networks typically boost performance in supervised learning, especially in language models, scaling up networks in RL proves to be a formidable challenge. It necessitates sophisticated strategies to ensure stable learning, such as the introduction of supervised auxiliary losses, distillation techniques, and pre-training. Moreover, it appears that deep RL networks do not fully utilize their parameters, which might explain the difficulties in enhancing performance through scaling. Simply increasing the number of parameters does not automatically translate to better performance unless these parameters are effectively employed. In the realm of supervised learning, architectural innovations like transformers, adapters, and mixtures of experts, MOS, have been pivotal for scaling models, particularly in natural language processing and computer vision tasks. MOS, with their modular nature, are especially significant for scaling networks to handle billions or even trillions of parameters, as they facilitate distributed computing and introduce structured sparsity into the network. This type of sparsity has been shown to enhance network performance in certain contexts. In our paper, we explore how the integration of MOS affects the scalability of parameters in value-based deep RL networks, specifically questioning whether performance improves with an increase in parameters. We find that incorporating soft MOS significantly boosts the performance of various deep RL agents, with the degree of improvement scaling with the number of experts utilized. To deepen our understanding of these findings, we conduct a series of analyses examining different aspects, such as gating mechanisms and input tokenizations, and investigate the properties of the experts' hidden representations, including dormant neurons. These investigations provide empirical evidence supporting the performance enhancements brought about by soft MOS. Looking ahead, we present promising directions for future research, including the application of MOS in deep RL networks. For example, we show preliminary results where soft MOS outperform baselines in offline RL tasks, assess their performance in scenarios with limited data, and suggest that exploring diverse architectural designs could be a fruitful avenue for further exploration. Moving on to the basics, reinforcement learning is typically used in scenarios requiring sequential decision-making, aiming to discover optimal behavior within a specific environment. These environments are often modeled as Markov decision processes, MDPs, characterized by a set of states, available actions, a transition function, a reward function, and a discount factor. An agent's policy maps states to a distribution over actions, and the value of a state under a policy is the expected sum of discounted rewards from that state onwards. The state action function quantifies the value of taking an action from a state and then following the policy. For large or infinite state spaces, function approximators like neural networks are employed to estimate these values. Our work primarily utilizes the newer Impala architecture for this purpose, though we also compare it with the original CNN architecture used in DQN. Additionally, DQN's use of a replay buffer and the concept of a replay ratio are crucial to our analyses. We also reference Rainbow, an extension of DQN that incorporates multiple algorithmic improvements, as a significant baseline in our research into deep RL. Section Summary. In this section, we delve into the realm of deep reinforcement learning, RL, where the integration of deep neural networks with reinforcement learning algorithms has shown remarkable success in achieving superhuman performance in complex tasks. While larger networks have been proven beneficial in supervised learning, scaling networks in RL poses challenges and requires specialized techniques like supervised auxiliary losses and pre-training to stabilize learning. By incorporating mixtures of experts, MOEs, into value-based deep RL networks, we observe significant performance enhancements as the number of experts increases, showcasing the potential of MOEs in improving deep RL agent performance. Section: Mixtures of experts. In this section, we delve into the concept of mixtures of experts, or MOEs, which have become a cornerstone in the design of most modern large language models, LLMs. These models are essentially composed of a group of expert subnetworks. These experts are selectively activated by what's known as a gating network, or a router, which directs each incoming piece of data, or token, to a certain number of experts. Typically, the number of experts an incoming token is routed to is less than the total number of available experts. In our case, we focus on routing each token to just one expert, which leads to what we call sparser activations. This approach of having fewer active experts at any given time helps in speeding up the processing time and allows for the computation to be spread out across different machines, making it a preferred method for training large language models. Instead of using the standard dense layers found in transformer models, MOE modules are used, which has shown impressive results in recent research. However, assigning tokens to experts in a rigid manner can lead to several issues, such as instability during training, loss of tokens, and challenges in scaling up the number of experts. To mitigate these problems, a variant called Soft MOE was introduced. Unlike the traditional method where tokens are assigned to experts in a fixed manner, Soft MOE allows for a more flexible assignment by calculating a mix of weights for each token across all experts and then averaging their outputs. This method is fully differentiable, making it easier to integrate into training processes. Let's break down how Soft MOE works in simpler terms. Imagine we have a set of input tokens, each with its own set of features. Each expert in the Soft MOE layer processes these tokens individually, with each expert having its own set of parameters. The inputs to the experts are a weighted average of all tokens, and the output from each expert is then combined based on another set of weights to produce the final output. The key point here is that the weights used for dispatching tokens to experts and combining their outputs are learned parameters, which allows the model to adaptively decide how much attention to pay to each expert's opinion. Our exploration into MOEs doesn't stop there. We also discuss how we've incorporated MOE modules into architectures based on Deep Q networks, DQN, for reinforcement learning. Specifically, we've chosen to place the MOE modules in the penultimate layer of our networks, effectively increasing the layer's capacity by a factor equal to the number of experts. This decision is illustrated in our architecture diagrams and is based on the common practice of replacing dense layers with MOEs in transformer models. When it comes to defining what constitutes a token in the context of our deep reinforcement learning networks, we've adopted a strategy commonly used in vision tasks. We treat each d-dimensional slice of the output from convolutional encoders as a separate token, allowing us to process these tokens through our MOE modules. This method of tokenization, along with a final linear projection to maintain the token size, has proven to be effective and intuitive. Lastly, we explore two main flavors of MOE architectures: the top K gating mechanism, with a focus on the simplified strategy of activating only one expert per token, and the Soft MOE variant. While the top K approach is more commonly used, our findings suggest that Soft MOE, with its ability to engage multiple experts per token, offers a promising balance between computational efficiency and model performance. This makes Soft MOE an attractive option for enhancing the capabilities of our baseline models. Section Summary. In this section, we delve into the concept of mixtures of experts, MOEs, which are integral to modern large language models, LLMs. MOEs consist of expert subnetworks activated by a gating network, enabling sparser activations for faster inference and distributed computation. Soft MOE, a differentiable soft assignment of tokens to experts, has shown improved trade-offs between accuracy and computational cost compared to other MOE methods. Section: Empirical Evaluation. In this section, we delve into the empirical evaluation of our study. We concentrate our efforts on examining DQN and Rainbow, two cornerstone value-based agents in the realm of modern deep reinforcement learning (RL) research. It has been shown in recent studies that adopting the ResNet architecture over the traditional CNN architecture leads to significant empirical improvements. Therefore, we conduct the majority of our experiments using the ResNet architecture. Following the methodology of the original papers, we assess the performance on 20 games from the Arcade Learning Environment, ALE, which is known for its diverse and challenging pixel-based environments. Our experiments are carried out using the dopamine library, which introduces stochasticity to the ALE through sticky actions. We adhere to recommended practices for statistically robust performance evaluations, particularly focusing on the interquartile mean, IQM. Each experiment was conducted over 200 million environment steps, with 5 independent seeds, unless stated otherwise. We present our findings with 95% stratified bootstrap confidence intervals. All experiments were performed on NVIDIA Tesla P100 GPUs, taking an average of 4 days to complete. Moving on to the aspect of parameter scalability, we explore the effectiveness of Top1Mo and SoftMo on DQN and Rainbow by integrating the respective Mo module in place of the penultimate layer and adjusting the number of experts. Since each expert is essentially a duplicate of the original penultimate layer, this modification effectively multiplies the number of parameters of this layer by the number of experts. To make a direct comparison in terms of parameter count, we also experiment with simply expanding the penultimate layer of the base architectures by a factor corresponding to the number of experts. Our findings reveal that SoftMo significantly enhances performance, and this improvement escalates with an increase in the number of experts. For example, in Rainbow, boosting the number of experts from 1 to 8 leads to a 20% improvement in performance. Conversely, enlarging the layer in the base architectures results in a performance decline. Specifically, in Rainbow, increasing the layer size from 1 to 8 causes a roughly 40% decrease in performance. This outcome aligns with previous research indicating the challenges of scaling up deep RL networks. While Top1Mo shows some benefits when added to Rainbow, it does not demonstrate the parameter scalability observed with SoftMo. It is acknowledged that deep RL agents struggle to maintain performance when scaling the replay ratio without specific interventions. Our observations confirm that SoftMos maintain a significant advantage over the baseline even at high replay ratios, underscoring their efficiency in terms of parameter usage. Regarding the number of experts, it has been argued that this is the most efficient way to scale models in supervised learning settings. Our results support the notion that SoftMo benefits from an increased number of experts, whereas Top1Mo does not. When it comes to the dimensionality of experts, our experiments show that simply scaling the corresponding layer in the base architectures does not achieve the performance levels of SoftMos and may even degrade performance. We experimented with reducing the dimensionality of each expert by the number of experts, effectively aligning the number of parameters with that of the original base architecture. This approach demonstrates that SoftMo maintains its performance advantage, even with significantly smaller experts, suggesting that the benefits are largely due to the structured sparsity induced by SoftMos rather than the size of each expert. Lastly, we examine the gating and combining mechanisms of Top1Mos and SoftMos, which employ learned gating mechanisms, albeit different ones. Top1Mo uses a top1 router to select an expert for each token, while SoftMo assigns weighted tokens to expert slots using dispatch weights. The learned combiner component then merges the outputs from the Mo modules to produce a unified output. If we use a single expert, the primary distinction between the base architectures and the Mo variants lies in the additional learned parameters from the gating and combination components. Our findings suggest that the majority of the benefits from Mos stem from the synergy of the gating, combining components with multiple experts. Interestingly, even a single expert SoftMo configuration yields performance improvements for Rainbow, indicating that the learned matrix plays a beneficial role. This is further confirmed by our experiments where replacing the learned matrix with a random one resulted in different outcomes. Section Summary. In this section, we empirically evaluate the effectiveness of incorporating text RM, Top1Mo, and TextRM, SoftMo, into DQN and Rainbow agents by replacing the penultimate layer with Mo modules and varying the number of experts. We find that TextRM, SoftMo, consistently outperforms TextRM, Top1Mo, showing significant performance gains that increase with the number of experts, while the base architectures struggle with parameter scalability. Additionally, we observe that the structured sparsity induced by TextRM, SoftMo, plays a crucial role in maintaining performance, even with smaller experts, highlighting the importance of the gating and combining mechanisms in enhancing deep RL networks efficiency. Section: Tokenization. In this section, we delve into the topic of tokenization. Primarily, we concentrate on exploring per-conv tokenization, but we also take a look at two other types, per-feet and per-samp. To put it simply, per-feet is like flipping per-conv on its side, creating D tokens each with a dimension of height times width, while per-samp treats the entire output from the encoder as a single token. When we look at the visual representation in our study, it's clear that per-conv pairs well with SoftMo, whereas Top1Mo seems to get more out of per-feet. Moving on to the encoder, our experiments mainly use the encoder from the Impala architecture. However, we've confirmed that even with a standard CNN architecture, SoftMo still enhances performance. Regarding game selection, to ensure our findings weren't just lucky outcomes from a small sample, we expanded our study to include all 60 Atari 2600 games, running tests with 5 independent seeds, similar to what previous studies have done. The results, shown on the left panel of our comprehensive game suite figure, indicate that SoftMo improves performance across the board. A key point of differentiation between the two Mo variants we're looking at is how they activate experts. Top1Mo activates only one expert per forward pass, a method known as hard gating, which can make training tricky. Many studies have suggested using load balancing losses to mitigate these issues. We tested this by incorporating load and importance losses into Top1Mo, but our findings, as illustrated, suggest that these adjustments aren't enough to significantly boost Top1Mo's performance. This implies that reinforcement learning agents might perform better with a weighted mix of tokens rather than relying on hard routing. In our additional analysis, we've shown that deep reinforcement learning agents using Mo networks are better positioned to scale up, but the reasons behind this weren't immediately clear. We decided to focus on 3 aspects that are often linked with training instability in deep RL agents: the rank of the features, interference between per-sample gradients, and dormant neurons. By conducting a detailed study on the Rainbow agent using the Impala architecture and employing 8 experts for the Mo modules, we tracked the norm of the features, the rank of the empirical neural tangent kernel matrix, and the number of dormant neurons, all with a batch size of 32. Our observations reveal notable differences between the baseline architecture and those incorporating Mo modules, with the latter showing higher numerical ranks of the empirical NTK matrices and almost no dormant neurons or feature norms. These results suggest that Mo modules help stabilize optimization dynamics, though we stop short of claiming a direct cause and effect relationship between these metrics and agent performance. Looking ahead, we focused on evaluating DQN and Rainbow with SoftMo and Top1Mo on the standard AIL benchmark to thoroughly investigate the performance improvements and potential reasons behind them. The positive outcomes we've observed lead us to believe that these approaches could be beneficial in other training scenarios as well. We've provided strong empirical results across various training regimes, hoping these findings will point to promising directions for future research. In the realm of offline RL, where agents are trained on a fixed dataset without interacting with the environment, we incorporated Mo's. Following established practices, we trained agents across 17 games and 5 seeds for 200 iterations, with one iteration equating to 62,500 gradient updates. We evaluated using datasets that comprised 5%, 10%, and 50% of the samples randomly drawn from all environment interactions collected by a DQN agent trained for 200 million steps. Our findings, as shown, indicate that combining SoftMo with 2 modern offline RL algorithms achieves the best overall final performance. Top 1 Mo also shows performance improvements when used with one of the algorithms, but not the other. Similar improvements were noted when using 10% of the samples. Section Summary. In this section, we primarily focus on text RM per conv tokenization and explore two other types, text RM per feat and text RM per samp. We observe that text RM softmo works best with text RM per conv, while text RM top 1 Mo benefits more from text RM per feat. Additionally, we investigate the impact of the number of active experts in Mo networks, highlighting that hard gating in text RM top 1 Mo may lead to training difficulties compared to the soft activation of all experts in text RM soft Mo. Section: Agent Variants for Low Data Regimes. In this section, we explore different approaches for adapting agents to work with limited data. Traditionally, agents like DQN and Rainbow are trained with millions of interactions within their environments. However, a new benchmark has been introduced that evaluates these agents with just 100,000 interactions across 26 games. We focus on two agents optimized for this scenario: DRQ, Epsilon, which is a variant of DQN, and DER, which is based on Rainbow. Our findings show that when these agents are trained with only 100,000 interactions, there's no noticeable difference in their performance. This suggests that the advantages of using mixtures of experts, MOs, only become apparent with a significantly larger amount of data. Yet, when the training is extended to 50 million steps, both agents, especially DER, show improved performance. We also delve into our proposed architecture that incorporates MOs right after the encoder, replacing the traditional feed-forward layer. This setup involves having each expert consist of a single feed-forward layer. We examine three different ways to integrate soft MOs with DQN and Rainbow, using the Impala architecture. The first method, BIG, involves each expert being a complete network on its own. In DQN, each expert has its unique final linear layer, whereas in Rainbow, this layer is shared among all experts. The second method, ALL, applies a separate soft Mo at every network layer, except the last one for Rainbow. The third method, regular, is the standard approach used throughout our study. For the BIG and ALL configurations, we route inputs at the beginning and use per-samp tokenization. We initially chose not to apply L2 normalization to the soft Mo layers for small tokens, based on previous findings. However, given the full input tokenization in BIG and ALL, we revisited the impact of L2 normalization. Our results indicate that excluding regularization, as done in most of our experiments, yields the best performance. Interestingly, normalization appears beneficial for BIG experts, particularly in DQN, where it even outperforms the regular setup. This difference likely stems from whether the last layer is shared. The approach of using separate Mo modules for each layer, ALL, doesn't seem to offer significant benefits and, when combined with normalization, results in agents that struggle to learn. Mixtures of experts, MOs, were initially proposed to scale language models to trillions of parameters by enhancing modular training and improving parameter efficiency during inference. MOs have also been applied in computer vision to scale vision transformers, reduce inference computation costs, assist in continual learning, and address multitask challenges. They have shown promise in transfer and multitask learning by specializing experts in subproblems and improving statistical performance. While MOs have been explored in reinforcement learning, RL, for both single and multitask learning, these applications often differ from our approach, focusing more on orthogonal, probabilistic, and interpretable MOs. The issue of parameter scalability and efficiency in deep RL is significant. It's partly due to the inefficient use of parameters, as networks in RL tend to underutilize their capacity. Studies have shown that networks can become increasingly filled with inactive neurons over time, and a large portion of network parameters can be pruned without affecting performance. Periodic resetting of network weights and training networks with high levels of sparsity have been demonstrated to improve performance. These observations highlight the need for strategies that better utilize network parameters, such as employing MOS, which we found to significantly reduce the number of dormant neurons across various tasks and architectures. Unlike previous efforts that focused on algorithmic methods for scaling networks in DeepRL, our work emphasizes alternative network structures to enhance scalability and robustness.